Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today another great hangout is in store. We're going to be talking about the star known as Beta Pictoris, or Beta Pic, which has been discovered to have one of the first stars discovered to have a debris disk or a ring of material around it, in orbit around it, which many astronomers believe planets are forming from. So we're going to, and the Hubble Space Telescope has been looking at this system for quite a while now, and we have the latest observations to discuss with the astronomers who made them. But before I get started with that, I want to remind everybody that this is the internet, not TV, so we want you to interact with us. Please leave us comments and questions, and you can do that in the form. The easiest way to do that is to use the Q&A app. It's just a button right there on the window that you're watching this from. You click on it, you leave a comment or a question, and I will see it, and I will get it to the astronomers as we go along. You can also comment on the YouTube and G+ pages as well. And if you're a tweeter, but not a twit, you can use the hashtag Hubble Hangout, and we'll be looking at that as well, so you can leave comments and questions that way. Now, before I also have a quick announcement I want to make. If you love Hubble and you know it, and you want to do more than clap your hands, you can do it by entering into the Ode to Hubble video contest. It's going on at spacatelescope.org. I've got the link to it in the description box. Make a video. Tell us how great you think Hubble is. If it's 3 minutes or less, you can be entered into the contest, and you could win some pretty great prizes. They're giving away a piece of the solar array that was taken from one of the servicing missions. So that's a really cool prize, and it's definitely worth doing. So head on over to the Ode to Hubble video contest and enter your entry soon, because I believe it's going to be closing in March, and voting will begin. So there you go. Also, if as many of you are aware, if you watch these hangouts every week, Hubble is turning 25 this April. It's been in orbit 25 years, and we've set up a website in honor of that, hubble25th.org. That's hubble25th.org. Visit there to learn about all things Hubble 25. So that would be, let us know what you think. Leave us comments and questions on that as well. Okay, so we'll get started. With me, as always, doing these hangouts is Dr. Carol Christian. She's the HST project scientist, outreach scientist, and Scott
Hello.
Lewis, our driver of the internet. Welcome, guys. It's good to see you again. We're back.
You too. We are back.
So
We're back.
So, Carol, I wanted to kind of revisit something we did last week. Last week we did on our hangout, we showed you the hubble25th.org site, and there was some confusion on some of you about the Flickr feed versus the images tab that we had on there, and I wanted to clarify that the Flickr feed on that site is basically one image from every year of that Hubble's been in operation during that particular year. So we have all the way back to 1990, some of the first images that were ever taken and gone forward. The images tab on that website, however, is a selection of images chosen for their beauty, their scientific importance. And if you go to that site and you click on the images tab, what you're going to see are really beautiful images that each one, if you click on them, will have a PDF file that's suitable for making a poster out of. So it's really kind of cool. There's also a video associated with each one as well. So I wanted to kind of clarify the difference between those two things in the website. And Carol left, so I guess that's...
No, I'm back. I'm sorry.
Okay.
I quit. No.
I'm done.
Right. No, so the Flickr site is one per year. It's an annual, so one image for 25 years, and the other are more, a group of us got together and we picked out what we thought were the best representations of images covering every type of observation that the Hubble is able to make. And so, and they come with the posters and everything, so if you want to print out a poster and make a display of your own, there they are.
Yeah, it's really cool. And I think you made a comment to me before the hangout started last week that they're kind of arranged in distance from the Earth, aren't they? So
yes.
the closer objects are listed first, all the way out to the most distant galaxies. So definitely check it out. Hope that clarifies things.Hank you for your questions and asking about those, and go check them out. Okay, so this week we are going to be talking about a star known as Beta Pictoris, or Beta Pic as we call it affectionately. In 1984, it was discovered to have a cloud of material, a disk of material in orbit around it. Astronomers call those debris disks. And the Hubble Space Telescope has been very active in observing these. It's made many observations of this system. And in 2009, it was discovered to have a Jupiter-sized planet in orbit around it, and there may even be more. So, but they're still doing some observations with that ongoing. So with me to talk about these things is Dr. Mark Kushner. He's from NASA Goddard. He's an astronomer there. Hi, Mark. Also with me is Daniel Apai and Glenn Schneider. They're at the University of Arizona. They were co-investigators, all three of them, on this issue. And so let me start with you, Glenn. Tell us a little about, before we get into the observations themselves, I kind of want to get a debris disk 101 lecture out. Not a lecture, but some information out. What are debris disks, and how common are they in stars?
So debris disks are disks of material that is basically replenished in a circumstellar environment from collisions of materials like planetesimals and asteroids and other such things that are orbiting around stars. It's not the primordial material that you hear about in protoplanetary disks. It's evolved from there. How common they are, we actually don't know. That's one of the big questions. Although we do see quite a number of them through their thermal infrared excess. Debris disks were originally discovered not by imaging, but by the IRAS satellite, seeing excessive thermal infrared emission over what you would expect from a star. And then observations started to try to look at these things. And Beta Pictoris was the first one where we saw light scattered by this fine pulverized material that makes up this debris field that surrounds the stars.
Okay, so let me make sure I understand what you're saying. So a protoplanetary disk is a primordial part of the star formation material, right? It's way before, and a debris disk is just debris that comes along much later, maybe from things colliding with each other, or
yeah, primordial disks, that protoplanetary disks are actually in an earlier phase. They're gas rich. There's a fair amount of gas and dust mixed in. By the time you get into this debris phase after the planets have formed, in the disks that we see, a lot of them are gas depleted. They may not be gas free completely, but we're in a different phase in the evolutionary state of the solar system. The disks influence the planets, and the planets certainly influence the distribution of the dust that makes up the disks. In fact, one of the things we look for in the scattered light signatures is asking the question, where are the planets? Because they kind of sculpt the material and force it into different places.
And now, this particular system, Beta Pictoris, it was discovered in '84, I believe, to have this debris disk. And as you said, they're very reflective in the IR. But this one's really bright, isn't it?
It is. It's extremely bright. It's very massive in terms of the dust component in the system. In fact, Beta Pictoris was first discovered as having this reflective, highly reflective dust in observations made by Brad Smith and Rich Terrell on a 2-meter ground-based telescope. It was actually at 0.9 microns, a little beyond the visual range. But Brad, I've spoken with him, he actually saw the Beta Pictoris disk in an eyepiece in a telescope. It's physically possible to do. I think he's the only person who's actually ever done that. So
wow, that's bright. So that is bright.
I've seen one.
So obviously this is in the optical if people are looking at it through eyepieces and stuff like that. That's
That's kind of a unique case. Most ground-based observations today, in fact, most of the ground-based observations today are in the short wavelength near infrared for imaging of the scattered light. There are some new capabilities, like with a particular system called MAG-AO that's pushing down into the optical. From space, with Hubble right now, we're doing optical imaging. We can get into the instrument in that, but we've done optical and near-infrared debris disk imaging from space.
Okay, and Daniel, do you have anything you'd like to add to that? Or does that pretty much cover it?
Yeah, in terms of the debris disks, Glenn mentioned the key points. So it's really basically when we are observing debris disks, they give us insights into the early evolution of a planetary system. In the case of Beta Pictoris, we can really see a system that's very young, and it's also a unique system because we know already that there is a planet in it, which was image that you mentioned. In most other cases, we know that there is dust, but we don't really know whether there is a planet in the systems or not. One very interesting aspect of this is that detecting disks is actually much easier than detecting planets directly. So we have a much larger number of disks that we already detected, but around stars around which we can actually try to figure out whether or not there are real fully formed planets.
Now, is that because they are just more? There's just more surface area to these disks than would be a planet.
Are very large, so they can be 100 to 1,000 times larger than the Sun-Earth separation, an astronomical unit. So in diameter, and that basically translates to a huge surface area which is reflecting back the light from the star. So
now we have a schematic of this system. I wonder if Scott, if you get a moment, if you could pull that up when you get a chance, so we can kind of show people what we're talking about here. So debris disks, as you said, Daniel, are they're much easier to see and detect than planets. Right now, the biggest way that we detect planets is by using, there he goes, he's got it up now, is by using the transit method to see them, to infer their existence by a dip in brightness of the star. So this is Mark, can you give us a little step through of this system here? What are we looking at?
Sure. Well, one thing I wanted to add was that there was.
Oh, okay. Go ahead.
There is a amateur astronomer who imaged Beta Pictoris with his home equipment. Can I post something to chat and people will see it?
Not in our chat window, no. But you could post a comment on the G+ page if you want, or do you have a link?
Someone.
Okay.
Or if you put it in the chat, I'll put it.
Yeah. Yeah. Scott can drive it for us. Okay. Yeah, that's pretty cool. Wow.
If anybody has some really nice amateur astronomy equipment, a telescope, it's within reach if you live in the southern hemisphere.
Look at that. Yeah, you can really see it right there. It's these images that you're showing now, and I don't want to get too far into this without explaining some of the things we're looking at. This one is occulted. It looks like the brightness of the star has been occulted. Am I right? Is that what Hubble does as well?
Yeah, you really have to do something about that bright starlight, which once it gets into your telescope, gets scattered around and bounces off all the various surfaces and struts inside the telescope, and can really very easily swamp the image of the disk and the image of the planet.
Okay, we'll return to this in a little bit later. I want to talk about the observations themselves, but let's go back to the system here. This is a sketch of the Beta Pictoris system. It's sort of a little diagram, a schematic of it, and it looks like it's tilted. Mark, can you comment on this a little bit for me?
Right. So the Beta Pictoris planet is inclined with respect to the disk midplane by a few degrees, and that's made it an especially fascinating system for us dynamicists, because when you see a planet that doesn't line up with all of these planetesimals which comprise the disk, you expect the planet to interact with the planetesimals and sculpt them into interesting shapes. And indeed, we've made models of this situation, and we expect that the disk should become sort of folded in the center. I had this sort of piece of Kleenex, which I might be able to use to illustrate it.
Okay.
It makes a kind of a funny 3D pattern in the disk. But if this is the disk plane, you have to picture a. I'm just going to do one side of the disk. So imagine. So the star is going to be. This is just going to be one half of the disk, right? The star is going to be off to the star is going to be right on the edge of the screen here.
Okay.
But, we're viewing it edge on, and the planet is kind of tilted, and the planet's effect is kind of like this pencil kind of poking up in the side of the disk.
Okay.
You see how it's kind of twisted and warped like that?
Right. Okay, and that's the effect of the planet on the debris disk?
That's the effect of the planet.
Well, that went a lot better than it could have. I was better than I was hoping you weren't going to blow into it or anything. So that went that went a lot better.
Everybody else seems to have a cold, but me. I'm lucky, I guess.
Yeah, me too.
So there's no snot accretion going on.
And there's a clump right here.
Okay,
Very strong winds.
Okay, so the planet itself. Can you put the schematic back up just a minute for me, Scott? I want to see the. so the planet is actually pretty close to the star compared to all this other stuff in the debris disk, correct? I mean, it looks like it's really close in. Is that and these? What are these clumps off to the side? I mean, I know that you showed some of these clumps there. There's a what it's O clump, warp plus peak. Can one of you explain these? Maybe Daniel. Maybe I could get you to explain some of those terms.
So Beta Pictoris is, as you mentioned, it's a very bright disk, and it's a very exciting one for several reasons. One of them is that because it's seen edge on, it's relatively close, and it has a lot of dust in it. It's actually one target that is probably the best to study if we are interested in debris disk. And already the early observations reveal that this is not a simple disk, and as Mark demonstrated, there is a lot of structure in this disk. And the more we observe it, the more complex it turns out to be. What this sketch shows you is basically it synthesizes observations taken at various wavelengths that probe different components in the disk. So with HST, we can probe the really fine dust, basically cigarette smoke particle sizes. But if we use other facilities, like the Atacama Large Millimeter Array, we can probe larger grains, millimeter size, like small sand grains, or we can even probe actually gas in these disks. So all of these instruments have observed Beta Pic. Essentially, every instrument that could observe it has observed it. It's a very popular target. And they found substructure hidden in the disk in various locations. That's basically what the structure is shown. To explain you what the acronyms and abbreviations mean, MIR is a mid-infrared. That's basically 10 micron wavelengths. And that traces intermediate sized dust grains that are glowing because they are warm. And there are also clumps that you see identified as millimeter clump. These are large grains, millimeter sized grains detected by ARMA. Now, the interesting thing about these structures is not simply that they are there, but they trace different dynamical properties of the disk and the actual structure. So, for example, while small grains like cigarette smoke particles, size particles can easily move around in the disk and can be blown out just by light itself, for example, larger grains like the millimeter-sized grains, they stay pretty much where they formed. So the fact that all these millimeter-sized grains are actually concentrated in two clumps, we infer from that there is actually a ring of these millimeter-sized grains centered on the star that we see as two clumps because we see the system edge on. Now that ring is basically constantly replenished from collisions of minor bodies like asteroids, and while the small grains can move around in the disk, the millimeter-sized grains tend to stay there, so they allow us to trace where basically this asteroid concentration is located or where the collisions happen more frequently, one of the two.
Wow. Okay. So this, as you point out, this is one of the most observed debris disks, but in part because it's very bright, and also the system is relatively close to us. How far away is it?
So it's about 19 parsecs, which corresponds to around something like 70 light years.
Okay.
And it's also, so part of it, people observe it partly because it's easy to observe, relatively speaking. I mean, it's of course still challenging, but the other thing about it is that all these interesting structures that were hinting, basically all this distortion that Mark demonstrated, was hinting on the presence of a planet. And for about 15 years, people have tried constantly to find a planet, and it's not until 2003 that one single image was caught, and until 2009 that it was actually confirmed that this is indeed a planet. And interestingly, the location of the planet and its mass is matching what some modelers have predicted based on the disk structure. So it's a very interesting prediction that we were able to find a planet in the right place based on the structure of a debris disk, and that's
so it wasn't observed directly before it was known about. It was seen. It was inferred by the effect it had on the debris disk around it.
That's right, and that's basically an interesting aspect that hopefully will be applicable to many other disks, and that's something Mark has been working on for a long time.
If I can add one comment to what Daniel has just said, Beta Pic also is observationally unique right now in the sense that it's the only imaged debris disk in scattered light that we actually also imaged planet. There are about 23 debris disks that have been imaged in scattered light, mostly by Hubble. Beta Pic's the only one that we see the planet directly.
Okay, that was going to be my next question. Have we observed it directly? And you're saying we have. So how often? Let's get to the observations. Then Hubble. We've talked about Hubble observing this for a long time. This has been a widely observed debris disk. What are these latest observations that you're coming out with today telling you? First, describe what the observations are, and Scott has some of them up now, and then we'll talk a little bit about what you've learned. Who wants to comment? Mark or Daniel?
We all want to comment. We just have to decide who goes.
All right, go ahead. Since you are the first, since
Okay.
Daniel and Glenn are the first people on the press release, I'll have you guys start. Go ahead, Daniel.
I will give a quick intro, and then Mark and Glenn can contribute to if I miss something. So basically, what we set out to do was to explore better than previously known the inner structure of the disk, which is most affected by the planet, and also where we know the planet to orbit. We also set out to actually try something new that was not done before, and that is to actually we realized that these disks are not as static as people often think about them. We tend to think about celestial objects, as being timeless and not evolving on the timescales that we see. But interestingly, this planet, Beta Pictoris b, which that's how we call the planet, is actually on a very short orbit for a direct image planet, and that means that it's on 8 astronomical unit distance. The orbit is roughly 20 years. So we can see basically in our lifetime going around and affecting its environment. So we expect that the disk could respond on those timescales. In addition, we also know that every single dust grain that we see in this disk is orbiting the star itself. So actually, if we return to this disk and we observe it again, say 15 years later, which is what we did, we don't see the same dust grains in the same place. They have moved around a bit.
So these are HST STIS images. I just want to interrupt you for a quick second, Daniel. Carol, can you tell us what STIS is?
Yes. So STIS is the Space Telescope Imaging Spectrograph. So you hear the word spectrograph, so you think it only may take spectra, which is to divide up the light into different wavelengths or corresponding to different energies. And that's very useful for doing sort of forensics on objects. The other interesting thing about STIS is that it also allows imaging, and it is one of the workhorses of probably not as well advertised as, say, the wide field camera 3 or the advanced camera for surveys, because they take they mainly take images. But STIS is a very powerful instrument for looking at objects like this and all kinds of astronomical objects, and it has this finger in it which blocks out the bright light from an object so that you can look at things like debris disks and then study the objects really close to the bright object, which would dominate the data if that occulting feature wasn't there.
Yeah, good. I'm glad you brought that up, because that's
a very powerful instrument. And actually, the amateur image that was shown before has some kind of an occulter as well. That's the only way. I mean, it's like, when you're driving down, well, even if you're outside and say you're driving and it's either near dawn or dusk and the sun is, right down your road, you have to occult that.
Yeah.
I know in Baltimore we have all kinds of traffic jams because certain parts of our freeways turn right into the sun and it slows down. Everybody has to put their hand out to occult the sun and see the surroundings, and that's exactly the feature of the instrument.
Well, your sun visor is a sort of occulter. It's a weird shaped one. But
sort of, but
so that,
I find out that my fist works better.
So many things besides occulting, are you?
Well, yeah, but
So
unnecessary.
Carol's multi-tool of getting things done.
Yes, that's right, getting things. So that alludes to what Mark was talking about. We got to get the brightness of the star out. I'm glad you brought that out. Brought that up. And so, okay, so Daniel, so we had Scott, can you put this back up? We had 3 different epochs observations of Hubble going back to '97, another one in 2012, and then there was these most recent ones, which also include ALMA and ALMA CO. what are these? What? So, what you were initially talking about was when you go back and revisit these debris disks, you don't see the same thing. That's sort of where you left off. And you're right; they don't look the same. Although this bottom panel has more information in it. So, if you want to continue, I wanted to interrupt and get that out for the people to see.
Yeah, just to clarify, the Hubble observations were in 1997 and 2012. And in fact, it's a real tribute to STIS and to Hubble how stable the system really is.
Yes.
An instrumental system that allows us to go back over a 15-year time frame and re-reduce the images that were some of the first that were taken with the coronagraph with STIS and be able to compare them to the 2012 images. So the ALMA image was a little bit later on, the one in the bottom.
Okay, thanks for clarifying. Yeah.
Are the Hubble scattered light images with the same instrumental system at the same wavelength, reducing it as close as we can now with new techniques, going back the same way and comparing those two epochs and looking for changes. And Hubble allows us to do this because it is as stable as it is.
Okay, and so ALMA is a radio or sub-millimeter telescope, correct?
That's right, yeah.
Yeah,
okay,
one of the important points, I think, is that doing these sort of studies on multiple wavelengths is really important, and Daniel was talking about this. As kind of a first-order rule of thumb, the size of the particles that you're sensitive to is roughly the size of the wavelength that you're observing with. So when you're observing in the optical, you have sensitivity, as Daniel called them, cigarette smoke particles, but roughly sort of micron or even a little bit submicron size. When you're observing with ALMA, or sub-millimeter or millimeter telescopes, you're seeing the pebbles, you're seeing the millimeter size grains and larger. So in order to really get this sort of holistic view of the system, of the smallest to the bigger particles, you really have to observe at multiple wavelengths.
Oh, okay, very nice. So this clump on the bottom panel off to the right, that pink area, those are the bigger particles then, or is that, am I reading this right?
It's actually a surprise.
That was a surprise. How so?
This is not coming from HST. These are ALMA observations that were published separately. But that actually is gas, so carbon monoxide gas, which we see in addition to the dust. Most of the systems we would only expect dust to be present and not gas, because gas doesn't have a long lifetime when exposed to interstellar ultraviolet radiation. This system has brought many surprises. One of them is this dust and gas clump. Really, the CO gas is coinciding with the dust clump, and that is actually a really interesting aspect of the disk. So I mentioned that many of the structures that you see in the disk, the overall warp, the S shape, the butterfly shape on the sides, is actually consistent and fully explained by this Beta Pictoris B planet. But what you see on the right-hand side, there is this large asymmetry, this gas clump, and also an enhancement in dust. And that's something that structure is not coming from Beta Pictoris B. There is another, or at least we don't think it does, or models don't really predict that alone. There must be something else going on there. And because the gas and the dust grains that are seen there, they don't have actually a long lifetime. We are speaking here about maybe a century or so. What you see there had to be released very recently. So one of the proposals, the only explanation, but one of the proposals is that we see basically an aftermath of a major collision there, where a Mars-sized object was destroyed in the past few centuries.
Oh, really? So I'm going to bring up Adam Senergy's comment. He's got this is relevant to what you're talking about. He said CO doesn't hang around for millions of years. So what's forming the CO clump? And you're saying it was probably a relatively recent event that might have been the result of a Mars-sized collision.
Yes, so that is one of the two leading explanations, and these kind of time-resolved observations that we do, that we demonstrated now with Hubble, that we are capable of doing, they allow us to track events like this and basically see, for example, the changes that you would expect from a giant explosion, basically, and dust scattering to occur, or the removal of fine dust grains, or just the orbital motion of the collision-produced particles. So we can return to Beta Pic, and we will be able to further search for changes and test also this idea that recently a larger body was destroyed there.
Okay, all right. So there you good. Thanks, Adam. That's a good question, and looks like that was a surprise. I didn't expect to see that at all. So it's a good. ALMA is doing that, isn't it? I mean, now that these observations are coming in, we're getting so much more information from ALMA that it's just amazing. I'm always hearing something new coming out of that observatory, so it's really neat. Let me get to a quick question from Dan Buddha, and then I'll ask you some more stuff. But if the planets formed from the same dust from the nebula, can't planets form without a star? If the planets form from the same dust from the nebula, can't planets form without a star? So let's say you have a coalescing debris disk or protoplanetary disk, I guess in this case.
Yeah.
Can you get planets without stars?
Yeah, this is actually a very good question, and there are multiple answers to this. So yes, in theory, you could accumulate enough dust. What really happens, though, is that you build planets, especially Beta Pictoris. B is a gas giant, so the vast majority of its mass is actually coming from gas, mainly hydrogen and helium. And the best way to accumulate mass that can build up a planet or a star is in the universe is to let gravity act. So under its own self-gravity, matter can collect and condense and increase its density until it forms objects. Now we can actually calculate what is the mass that you need to be able, basically for self-gravity to be important enough that it concentrates mass. And it turns out that it's very difficult for really small objects, like a planet alone, to form in the interstellar medium of the star, because the mass that you need to form a planet doesn't have enough gravity to concentrate the mass. When you start to have enough mass that you concentrate it under its own self-gravity, then you are forming already stars. So we do expect to see a few, low mass stars, and we do see low mass stars, and even substellar objects, brown dwarfs. But we expect very few or no planet mass objects to form, especially speaking about rocky planets, without stars. That said, there are presumably a large number of planets that were ejected from a planetary system. So we would actually expect many planetary mass objects out there that formed in planetary systems and now
they formed in the normal way or the common way or whatever term you want to put, and then they were somehow ejected from their systems, going out on their own. It reminds me of Space 1999, where that happened to the moon somehow. Remember that show? Anyway.
I have a question. So I'm going to ask Glenn a question, which is earlier you were talking about the formation of stars and protoplanetary material, and then these debris disks. These objects are still not very old, right? I mean, this thing is, I don't know what, 12 million years old or something like that, which is really a baby in comparison with our sun and our sun system, right?
You're asking about Beta Pic in particular. It is about 20 million years old, sort of the best estimate now, which is relatively young. We actually do image and see debris disks about a gig a year, about 1 billion years old or so, and there are probably older ones as well. They get difficult in some sense to detect because we're looking at things that are fairly faint in surface brightness as you get older. There may be some evolutionary relationship there, but our own solar system has a debris disk. We live inside a debris disk. It's a 2-component disk. Now, all of the debris disks we've seen of this sample of 24 are the outer parts of these systems. They're equivalent to sort of our Kuiper belt in our own solar system. But they're hundreds or thousands of times more massive than our own, which is why we see that. We're able to get into that regime. If we were at Beta Pic looking back at our solar system with our current technology, we could not see our debris disk. But
right.
Out on a moonless night and you look inward and you see the zodiacal light, that's the inner component of our own debris disk. We can see that because we're close. You get out 10 parsecs and look back and you can't see it. So depending upon the amount of debris disks may be fairly common. They just get difficult to detect. But Beta Pic is a fair youngster at around 20 million years.
How massive is it? What kind of star is it?
It's an A star, A3.
A5.
A5.
Okay.
Yeah,
so it's a little more massive than the sun, and it's part of a group. I mean, the age. There's also a group. It's in a group or something, and they're all similar ages. Is that right?
Stars that are named for Beta Pic called the Beta Pic Moving Group.
Oh, look at that.
It implies they sort of have common space motion, which is a big clue that they're of common origin. In fact, there is a baby in size, not in age, debris disk around a star called AU-MIC, AU Microscopium,
Yeah.
which is the smallest mass star for which we have imaged a debris disk. It's about 0.3 solar masses. It's an
Wow.
But it's also around 20 million years old, and it's really interesting to study the two comparatively, because presumably they formed just at about the same time and in the same formative environment. So we have a discrimination there with mass. I see a picture of the AU-MIC.
There's AU-MIC right there.
I think we have AOMIC, yeah.
And by coincidence, it also is almost exactly edge-on as we see it, just like Beta Pic. So those are sort of coincidence things, but it gives us a nice probe in different stellar mass regimes, but within sort of common formation environments.
Are these STIS observations too?
These are also using STIS observations. They're epic around 2011, so they were taken about the same time as Daniel's more recent Beta Pic observation.
Oh, okay. So you were saying, I think it was Glenn that was saying that the presence of the planet in Beta Pic was sort of inferred before it was imaged directly. Is there any evidence of any other planets based on what you're learning about these observations from the debris disk? Do you think there's any other planets there, or are you not able to infer that yet?
Well, when you see a planet that's on an inclined orbit, you have to ask yourself, how did it get onto that inclined orbit? It's hard. The Beta Pictoris B planet is about 8 Jupiter masses, and it's hard to push around something that's 8 Jupiter masses. I mean, think about when you're driving on the highway, and you're driving in your little Volvo, and along comes a giant tandem trailer truck. You get out of its way because it's so massive, because you know that even if you crash into it at high speed, it's not going to stop. You're going to be the one who gets flung off the road. The same thing happens in a planetary system like the Beta Pictoris planetary system. You have this gigantic planet which is swinging around there, and yet somehow it's gone off the track. Somehow it's inclined with respect to the disk, and it's almost like you're coming along and you're seeing this train that's off the track, and it's a great big train, and you don't know what was so massive that was able to push it out of the disk.
So you're saying that because it's inclined is a strong signal that there may be something else out there that interacted with it.
Yeah, it suggests to me that it scattered off another planet. Now, I don't know whether that other planet is still around. The other planet that it scattered off may since have been swallowed by the star or been ejected into interstellar space.
Okay. Okay, so Adam Synergy has an interesting question. If we could see Beta Pic face on, would we see gaps or a spiral pattern in the disk? Who wants that one? Daniel?
I'll start by saying that's
okay.
a good question, and that's one of the things that we're trying to find out.
We'd love to know that.
So you might see a gap that's swept out by the inner planet, but there may be other features in there as well. You just don't know.
Yeah, because we see in projection, it's a bit difficult to disentangle the real 3D structure of the disk. And at the moment, we are able to make spiral-like models, spiral structure-like models that are consistent, but we can also make ring-like distributions with additional dust clumps that, if are turned right way, they would both explain the morphology we see. Time-resolved observations like the one we do now can help disentangling it, because depending on how far certain structures are from the star, they will have different orbital periods. So they will be located in a different place in projection when we revisit the system.
So the standard astronomy answer: more observations are needed, right?
I will say, when we were talking in
I was going to say that.
in the case of AU-MIC, the little baby disk in size we were talking about, we actually had observations over about a year apart, which is not a lot. But one of the things we saw in there, which is sort of intriguing, is that at about 13 AU, there's a big bump on one side of the disk above the disk plane, which actually moved out between the two observations. And again, this is being seen edge-on. And the question is, are we seeing Keplerian motion of some blob, or are we seeing sort of super Keplerian motion, maybe a pattern like a density wave or something, as we're talking about spiral structure? We need more observations for that, but we're seeing it with only 2 with AU-MIC. We've got to get back in and see it again.
Right. That's good. So good question, Adam. Thanks for that. So, well, are there more observations planned then? Are we going to be going back and revisiting this again?
I can tell you there's a Cycle 23 proposal in prep.
Okay. Well, we'll have. Hopefully, this hangout will give it a little more attention. So we'll see. Okay. All right. So,
I don't know if you have a question, or there's another interesting aspect that may be worth mentioning here.
Okay, go ahead.
Yeah. So debris disks are interesting because they help us to understand how planetary systems form and evolve. But they are also interesting for another reason, and that's something Mark has worked also extensively, is because they may or they will pose a limitation on what really small Earth-like planets we can image in the future. So we would all love to build a telescope, a large enough telescope that is capable of directly imaging Earth's twins. Now, as I mentioned, these disks have a very large surface area. So actually, these dust disks may outshine Earth's size and Earth-like planets around other stars if there is enough dust there, or if the disk is oriented in the right way, or they have the proper shapes. So for us to understand the diversity, the structure, and of disks and the processes that shape them is an important milestone towards figuring out which Earth-like planets we can observe and how we should build and design our telescopes in the future.
Well, I think you've just given me a segue into something I wanted to talk about with Mark. Mark, you wanted to bring up a citizen science project that is known as diskdetective.org. Is that going to sort of help address what Daniel was talking about? You want to talk a little bit about that?
Right. So the NASA's WISE mission brought home some spectacular images of the entire sky in the mid-infrared, very similar to the IRAS mission that Glenn was talking about that first discovered the Beta Pictoris disk. But the WISE data set is so vast, it imaged 747 million objects, that it's hard for us astronomers to look through it by ourselves. So
why is it? Let me just back you up. WISE is Wide Field Infrared Survey Explorer. Did I get right?
Yes. Perfect.
Awesome. Okay, good. That's in orbit right now. It's a wide field infrared telescope. Okay, and it's got a lot of data. Go ahead.
Right, a lot of data. So we have a big data problem. Somewhere in that data are a few thousand disks waiting to be discovered. Maybe some analogs of Beta Pictoris. So what
Scott has Scott. Let me just interrupt you. Scott has the website up, diskdetective.org. Go ahead.
Thanks. So we put the data online. We put a bunch of data online, and we asked for help identifying disks in the data. So if you go to diskdetective.org, anybody can go to this website, and in a few seconds you'll be looking at images of sources, which might be stars with disks, or they might be galaxies, or they might be asteroids, or they might be active galactic nuclei, or things that go bump in the night. Anything that glows at 22 microns. We're asking people to go there and look at these little 10-second videos and help us sort out what is what.
So you have example videos of what you're looking for and what you're hoping to see to kind of get people trained. Is that a big learning curve? How long do you think it'll take a typical person to get on track?
We have users from 6th grade to folks who are retired.
Okay, so this is a Zooniverse thing, and these guys have gotten this down by now. They really know how to get you going quickly with a minimum amount of effort. So if you've never done one of these before, they're a lot of fun, and they really do contribute, help astronomers contribute to discoveries in science. Is it going to be up for a certain length of time, or will it always be available?
So we're hoping to finish by the year 2018 when the James Webb Space Telescope launches.
Oh wow! Okay, that's a long time.
So, yeah, there's a lot of work to be done. So please hop over to diskdetective.org and help us find a new disk, and then we're going to call up Daniel and Glenn, and they'll take some images of it. With,
okay, cool.
Hubble.
Yeah, thanks for letting us know. Now, Glenn said earlier that there was a subset of about 24 of these. Is that just that's not all we know about, right? Those are just the ones Hubble's observed, correct?
That is the number of disks, actually 23, that
23,
have
sorry.
scattered light since the discovery of Beta Pic. We've been kind of wrong. It is a complicated technical challenge to observe these things. So there's not a lot that we have been able to observe so far, and that's even the new generation of ground-based extreme AO imagers is helping, but we're in the regime where it's tough. It's a really difficult observational problem. It's not as simple as just blocking the light. Beta Pic is great. Beta Pic is hugely bright.
Very obvious.
But as I think was said in the press release, it's a prototype, but it's not a great archetype for circumstellar disks. I mean, we're talking about systems with a lot less dust, which make them a lot harder to see.
Okay, now ordinarily with big data issues that Mark was alluding to, astronomers rely on software to automatically go through and identify sources or galaxies and things like that, but apparently this problem is a little more difficult, and the Zooniverse people, one of their specialties is they can get human eyeballs onto lots of human eyeballs onto things, because the human brain is very good at seeing patterns and recognizing what things might be. So definitely encourage you guys to get on board and check it out. They always do high quality work there, and this is your chance to find some more debris. 23, that's not very many. We need more than that, folks. So go out there and help us find more. Scott, I don't see any questions in the Q&A app. Do you have anything from Twitter?
I have a lot of people just saying how awesome it is, which is great. It is awesome.
It is awesome.
A lot of people just thinking it's absolutely beautiful, especially being able to add in with ALMA.
Yep.
Because as my radio astronomer friends would say, ALMA got you, and yes, yes it does.
Yeah, it's really revolutionized things. I can't believe and resolutionized things. You like how I did that with the
yeah, you're clever, man.
Well, that's why I do this. Okay, well, I guess that's about it. I don't see any other questions or comments, and I want to thank you guys for watching.
I did want to share an image real quick we didn't get to, but I think is fantastic.
Okay, fair enough.
And it really displays on what we're seeing and how we're seeing it.
Oh,
Okay.
that's nice, yeah.
All right, Daniel, you want to explain this to us a little bit?
So there it is.
Let me switch that.
Yeah, just click on Scott's.
Yeah, click on my thumbnail. This is showing the. We're seeing the plane. We're actually seeing how much of the warp's going on.
Yeah, that's right. So yeah, and maybe it's worth adding. So it's Beta Pic is the best system, probably the easiest to image in some ways, but still to get to this kind of image quality that we got, it was a 2.5-year effort to explore all this. But we were very happy because these observations allow us to probe the disk further in than it was previously possible in these wavelengths, and also give a very high quality image of the inner structure. And what you see here in particular, what we did is that we vertically stretched the image, so we basically expanded it by a factor of 4 in the vertical direction to emphasize the structure. And you see basically, let me walk you through this. In the outer parts, on both sides, both wings, you will see that the disk is opening up. That's called a butterfly asymmetry, and that is caused by fine dust grains that formed further in through collisions, and then they were blown out by the light of the star. And as you go closer in, you will see the width is basically around what I call cut A and cut D. It gets again a bit thinner, and then around cut B and cut C, these are just marking locations, it gets wide again and puffy. And that's basically the warp. That's the outer edge of the warp that is introduced by the planet. So the dashed line shows approximately the angle at which this that inner part of the disk is warped. And you see another dashed line, that's roughly the inclination, or best guess for the inclination of the planet's orbit. So it's very interesting that, and it was also predicted that even though the planet is just slightly misaligned with the disk, which, I mean, it's significantly misaligned, but it's not, you see, tens of degrees, but it will be able to move out planetesimals to a more inclined orbit and cause this large gap. Now, what we didn't know before is what happens really within that gap. And we see that within that gap, basically, the disk, again, converges back, the brightest part is converging back to the disk midplane. Yeah, thank you for pointing that out. And it gets thinner again, which is actually fully consistent with the model predictions how it should look. And it's interesting because there were some observations that were hinted on a different inner disk structure, but we basically see now clearly that it's matching with model predictions.
Awesome. Thank you. Thanks for reminding me about that, Scott, and putting that up. That's important. Yeah. I'm glad we got to it. So thank you very much. Okay, so a couple of comments just came in. This one's from Fredrik Ulfes. Will we ever be able to detect a heavy bombardment period around another planet? Or I'm sorry, around another star? There was a period, I guess, in our solar system's history where the Earth was bombarded quite heavily. Would we ever be able to detect that around another star? Anybody?
It's a great question.
We're hopeful, I guess, is the answer.
We want to.
We'd love to be able to. Whether we will or not, I guess it depends on a lot of factors, but it would be nice. And let's see. Bob Harkins, can we see the amateur astronomer pic?
I put it up on Twitter, and it's in the Google Plus event. So if you head over to google.com/plus Hubble Space Telescope, you will be able to see our event here. Or if you follow us on Twitter @Hubble Telescope, I've placed that in there along with a link to that website.
Yeah, and if you're not following us, then what is up with that? Come on now. You're just not cool if you're not following us. So yes, thank you for that. That was good. We didn't get a chance to get to a whole lot of that. So let's see. I've had Patrick Festa. I've had trouble signing into the universe in the past.
He meant Zooniverse.
I know. I can log into the universe every day.
Well, you have to do sudo sign in. You have to have the super user command to get in.
Yeah, all I can say is they generally have they do a very good job with their implementation. So I would just say if you have any issues, just let them know and they would get right to it because they've done this a lot. They've got this down pretty good, I think. Okay, folks. Well, I guess that's it for this week. Thank you guys for watching. We hope you'll come back next Thursday at the same Hubble time, same Hubble channel,
right,
where we will do another
Try
hangout.
a different browser.
Oh, what's that?
Try a different browser.
Try a different browser.
Yeah, a different browser might do it.
Okay, yeah. So
don't use Netscape Navigator. I think that's
Lynx doesn't work either. So
yeah.
Okay. All right, folks. Well, that's it. We hope you'll join us next Thursday. We will thank you for your questions and comments. And as always, on behalf of everybody here at the Hangout, keep looking up.
Thank you.
Bye, everyone.
Thanks. Bye-bye.
On that site is basically one image from every year of that Hubble's been in operation during that particular year. So we have all the way back to 1990 some of the first images that were ever taken and gone forward. The Images tab on that website, however, is a selection of images chosen for their beauty, their scientific importance. And if you go to that site and you click on the Images tab, what you're going to see are really beautiful images that each one, if you click on them, will have a PDF file that's suitable for making a poster out of. So it's really kind of cool. There's also a video associated with each one as well. So I wanted to kind of clarify the difference between those two things in the website. And Carol left, so I guess that's...
No, I'm back. I'm sorry.
Okay.
I quit. No.
I'm done.
Right. No, so the Flickr site is one per year. It's an annual, so one image for 25 years, and the other are more
long. You can also comment on the YouTube and G+ pages as well. And if you're a tweeter, but not a twit, you can use the hashtag Hubble Hangout, and we'll be looking at that as well, so you can leave comments and questions that way. Now, before I also have a quick announcement I want to make. If you love Hubble and you know it, and you want to do more than clap your hands, you can do it by entering into the Ode to Hubble video contest. It's going on at spacetoLescope.org. I've got the link to it in the description box. Make a video. Tell us how great you think Hubble is. If it's 3 minutes or less, you can be entered into the contest, and you could win some pretty great prizes or giving away a piece of the solar array that was taken from one of the servicing missions. So that's a really cool prize, and it's definitely worth doing. So head on over to the Ode to Hubble video contest and enter your entry soon, because I believe it's going to be closing in March, and voting will...
A group of us got together and we picked out what we thought were the best representations of images covering every type of observation that the Hubble is able to make. And they come with the posters and everything, so if you want to print out a poster and make a display of your own, there they are.
Yeah, it's really cool. And I think you made a comment to me before the Hangout started last week that they're kind of arranged in distance from the Earth, aren't they? There, so
yes.
the closer objects are listed first, all the way out to the most distant galaxies. So definitely check it out. Hope that clarifies things. Thank you for your questions and asking about those, and go check them out. Okay, so this week we are going to be talking about a star known as Beta Pictoris, or Beta Pic as we call it affectionately. In 1984, it was discovered to have a cloud of material, a disk of material in orbit around it. Astronomers call those debris disks. And the Hubble Space Telescope has been very active in observing these. It's going to begin. So there you go. Also, as many of you are aware, if you watch these Hangouts every week, Hubble is turning 25 this April. It's been in orbit 25 years, and we've set up a website in honor of that, hubble25th.org. That's hubble25th.org. Visit there to learn about all things Hubble 25. So that would be, let us know what you think. Leave us comments and questions on that as well. Okay, so we'll get started. With me, as always, doing these Hangouts is Dr. Carol Christian. She's the HST project scientist, outreach scientist, and Scott Lewis, our driver of the internet. Welcome, guys. It's good to see you again. We're back.
You too. We are back.
So we're back.
So, Carol, I wanted to kind of revisit something we did last week. Last week we did on our Hangout, we showed you the hubble25th.org site, and there was some confusion on some of you about the Flickr feed versus the images tab that we had on there, and I wanted to clarify that the Flickr feed... Hello, everybody, and welcome to this week's Hubble Hangout. My name is Tony Darnell. I work at the Space Telescope Science Institute, and today another great Hangout is in store. We're going to be talking about the star known as Beta Pictoris, or Beta Pic, which has been discovered to have, one of the first stars discovered to have a debris disk, or a ring of material around it, in orbit around it, which many astronomers believe planets are forming from. So we're going to, and the Hubble Space Telescope has been looking at this system for quite a while now, and we have the latest observations to discuss with the astronomers who made them. But before I get started with that, I want to remind everybody that this is the internet, not TV, so we want you to interact with us. Please leave us comments and questions, and you can do that in the form. The easiest way to do that is to use the Q&A app. It's just a button right there on the window that you're watching this from. You click on it, you leave a comment or a question, and I will see it, and I will get it to the astronomers as we go along.